Welcome to solverfy.
We are told that we have two rays traveling parallel to the principal axis and strike a large plano-convex lens that has an index of refraction N of 1.6. And the rays are traveling from an infinite distance away. So the object distance, which creates these rays, for both ray 1 and ray 2, which I indicate as subscript 1 and subscript 2, is equal to infinity. So the object distance, which I write as P, for the first ray, P sub 1 is equal to P sub 2, and they're both equal to infinity. It also says that the radius of curvature of the lens is R, and it's equal to 20 centimeters. And the two rays are at a distance h1 equals 0.5 centimeters and h2 equals 12 centimeters from the principal axis. And it wants us to find the difference delta x in the position where each point crosses this principal axis. And if you want to look at a figure of this situation, you can look at figure P23.54 to get a reference for what we're talking about here. So first, let's consider the ray at the position h1. So the ray at position h1, we're going to call that ray 1, and we're going to denote it by subscript 1. Okay, so if we're looking at this ray or considering this ray, we can use the refraction formula for a curved surface. And that refraction formula says that the index of refraction of the medium we're coming from, which is just air, so it has an index of refraction of 1, divided by the distance to the image, Q1, is equal to the minus the index of refraction of the lens, which is N, divided by the distance to the object, which is P1, is equal to 1 minus N. And since this is a convex lens, it's divided by negative the radius of the lens. Well, P1 is infinity, and anything divided by infinity is 0. So we're just going to let that equal 0. So that goes to 0. And solving for Q1 then, we find that Q1 is equal to R, or negative R, divided by 1 minus N. Or in other words, Q1 is equal to 33.3 centimeters. So now, if we find Q2, we will be able to figure out the difference between Q1 and Q2. And this will allow us to figure out that delta x value. Okay, so now we're going to consider the angle of incident, which I'm going to call I. And the sine of that angle, or the sine of I, is equal to the opposite over the hypotenuse. So this is equal to H2 divided by R. Again, we're looking at the second ray now because we want to find the distance to the image produced by the second ray, Q2, where it crosses that principal axis. So H2 divided by R, so that'd be 12 centimeters divided by R. This is equal to 0.6. So the sine of I is equal to 0.6. Okay. Therefore, if you solve for I, we find that I, so you just do the inverse sine, we can find that I is equal to 36.9 degrees. Therefore, we also know what the cosine of I is. So from this, we can infer that the cosine of I, or the cosine of 36.9 degrees, is equal to 0.8. And all this information will become important here in a second. Okay, so now we have the angle of incident. We can find the angle of refraction using Snell's law. We kind of ran out of room on this page, so we'll get a new page. So using Snell's law, we can find the angle of refraction. So the sine of the angle of the incident times N is equal to the index of refraction of error, which is 1, so we can just ignore that, times the sine of the angle of refraction, R. Or in other words, sine of R, we'll just plug in our values for N and the sine of I, which we had. We find that the sine of R is equal to 0.96. Therefore, r, so if we just take the inverse sine of both sides, we can find r, and we find that r is equal to the inverse sine of 0.96, which is 73.7 degrees. So that's our angle of refraction. Okay, so then the cosine of r, we can get from that. So cosine of that value is equal to 0.28. Okay, so since we know the sine of r and the cosine of r, we also know what the tangent of r is, right? Because the tangent of r, which is equal, so that's tangent r, is equal to the sine of r divided by the cosine of r. So sine of r divided by cosine of r is equal to 3.42. Okay. And also, similarly, we can find we can use this same type of thing to find the tangent of the incident angle, the tangent of I, and use that to find the thickness of the lens, which we're going to need. Okay, so the tangent of I is equal to the cosine of I, which we know, or excuse me, the sine of I, which we know, divided by the cosine of I, which we know. But using the fact that the tangent of an angle is equal to the adjacent over the opposite, using right angle formulas here. So that is equal to h2 divided by the radius of curvature r minus x. And here x is the thickness of the lens. Okay, so therefore we can solve for x. And we find that x is equal to h2 times the cosine of I divided by the sine of I minus r. Or in other words, x is equal to 4 centimeters. Okay, so now that we know x, we can go ahead and move on. And we're going to let the angle theta be the angle made by the light ray h2 at that position h2 with the horizontal. So we're going to let theta then, we ran out of room here, we're going to let theta equal r minus I. And tangent theta, or the tangent of r minus I, is equal to h2 divided by q2, the distance to the image produced by the h2 ray, plus x. And that's just using, again, the fact that the tangent of an angle is the opposite over the adjacent. Okay? So then we can solve for q2 here because, remember, tangent of theta is the tangent of r minus I, right? So if you go back here, we found that r is 73.7, and we also found on over here that I is equal to 36.9. So theta is equal to 36.9 degrees. So q2, solving for this, is equal to h2 divided by the tangent of theta minus x. which is the thickness of the lens, or 4 centimeters. So we find that Q2 is equal to 12 centimeters. And lastly, now that we have Q1 and Q2, which is the position in which the ray at point H1 and the ray at point H2 cross that axis, we find that delta X is equal to Q1 minus Q2, which we know both of these now. Plugging in those values, we find delta X is equal to 21.3 centimeters. And we can box that in as our solution to our question.